So this lecture, we will discuss about global navigation satellite system applications in geosciences. And I am P.K. Champati Ray from Indian Institute of Remote Sensing. And we'll be discussing on dynamic Earth. That is the reason why the global navigation satellite system is critical for various earth sciences applications. We will briefly touch upon the plate tectonics, earthquake, active fault, dam and bridge safety, crustal deformation, tectonics, total electron content as earthquake precursor. Some of the applications of GNSS in geosciences will be covered. Now, we will say that the strong reason for using the global navigation satellite system, primarily due to the planet Earth is very, very dynamic. We have the dominant role of plate tectonics on the planet Earth, and this is unique to so far. It is so far as per the discovery which has been made till now. The planet Earth has number of plates which are in constantly move. So that's the reason that everything is moving on the planet Earth. And wherever you are sitting, wherever you are attending this lecture, every point is actually moving, and you can calculate how much it is moving using a precise GNSS based observation. So that makes really things interesting, that when everything is moving and moving at a very, very slow rate, the velocity could be as low as 4 to 5 millimeter a year, and it can go up to as high as something like 170, 180 millimeter per year. So this movement rate across the globe is different it is different at different places. And if you take the time scale, ever since the formation of the Earth, almost 4.5 billion years ago, since then, this movement is also highly variable. So it depends on which plate we are talking about. So each plate has its own variable rate of motion ever since the plate started moving. And so far as the geological knowledge and the observation analysis goes, the Indian plate on which we are all, our country is located. So Indian plate is moving something like 55 millimeter a year, 50 to 55 millimeter a year. And it is moving in the northeast direction. And this movement, has resulted in the collision of two plates, Indian plate as well as the Eurasia plate, consisting of Europe and the Asia, that is Russia, China, and those countries. They belong to one plate and we belong to another plate. Because of the collision of the plate, the gigantic Himalaya has come into existence. This is just to illustrate the dynamic nature of the planet Earth. And like Indian plate and Eurasia plate, there are large number of plates. There are smaller plates and the larger plates. We will look into details, and everything is constantly on move. And because of the movement of the plate, we have a lot of repercussions. So the primary repercussion is in the form of the earthquakes, the volcanic eruptions. So those are the two important things what comes to our mind when we discuss about the plate tectonics. Apart from that, there are many other relevant important applications. But within this 1 hour, 10 minutes, 15 minutes lecture, I will try to touch upon this critical aspect of the earth science. Now, if you see on your screen, this that's the reason why the GNSS, which is very, very good for the precise measurement, is important, because planet Earth is on a move. And if you see the planet Earth consisting of principally three layers. So one is the solid inner core, we have the fluid outer core, then we have a mantle and the crust. And so the core, mantle, crust, what we see today, crust is the thinnest outer layer, and on which the continent and the ocean, land mass and ocean is situated, and along with the plate, these are also moving. Now, the number of plates, what I was telling, every part of the planet Earth consists of number of plates. So we have the prominent plates. There are 8 major plates, and the theory of the plate tectonics, which was first published in 1915 by the Alfred Wegener. People did not believe when he said this Earth consists of number of plates. So it took almost 50 to 60 years scientifically to prove that yes, the planet Earth consists of number of plates. So it was only in 1960s it was accepted, the theory of plate tectonics was accepted. So you can imagine that it's not very old theory. 1960s only it was confirmed. And if you look at the timeline, the GNSS came into existence in late 1980s and 1990s. It was established as a viable and one of the most promising technology, space-based technology for the monitoring of the movement. Basically, that comes from the precise measurement of the position on the planet Earth based on the satellite observations. So you see here the India-Australia plate. We have the Eurasia plate. I hope you can see my cursor. And this some of the movement direction is also provided. We have a smaller Arabian plate, African plate, Nazca plate, then the South American plate, North American plate, Caribbean plate, smaller plate. So like this, number of plates are there, and all they are moving in a different direction, and the rate of movement or the velocity and the direction both varies across the globe and also across the time scale. What I said from from the last, you can say the 100 million years. So now coming to the Indian plate. So this is one of the prominent applications of GNSS, Global Navigation Satellite System. I hope by now you have been introduced about the GNSS, various types of GNSS, and the satellite orbit. It works. Most of the satellites are located, and number of satellites are there. Different countries have different constellation of GNSS satellites. India has the IIRS or the NAVIC. And you have nowadays commercially available dual frequency receivers which can receive the signal, and some of the mobile phones also can receive the signal. So communication technology has advanced, and the processing techniques also have advanced. Relevant softwares are now available, and you can measure precisely order of few millimeters, so 2 to 3 millimeters accuracy. You can measure location of any place on planet Earth. And over a period of time, what we see for the Indian plate, at several locations attempts have been made. This is a paper which is published in Nature Scientific Report, one of the very important reputed journal, as you know, and the Indian Institute of Science team and I will and other team, various other Indian scientists also have come with similar results. And I have just mentioned this paper because it was published in a prominent journal. So for reference purpose, you can see this paper, but similar observations have been taken by various agencies in the country, including Indian Institute of Remote Sensing. We have also our own set of instruments, dual frequency GNSS receivers across the Himalaya we have installed, and also we have access to global initiative that is the International GNSS Services, so which also has across the globe and provides the data to all the scientists. Now, so what you get here is some kind of a translational motion towards the north-northeast direction, and so So that is because of that Indian plate was somewhere along with the Antarctica plate, somewhere down south in the closer to the Antarctica. And last 70 million years, it has made a journey and it has come all the way to hit, collide along the Himalayan arc with the Eurasia plate, resulting in the gigantic, Himalayan mountain, which goes up to 8 kilometers high. So that much is the collision effect because of the plate tectonics. Until the collision is still continuing, the impact in the form of the earthquakes and other impacts we have been experiencing even now, even today. So not only the Indian plate, if you look at we move on to the move on to the North America. There the nature of movement, what I have shown you is different. So we have a strike slip movement. So one plate goes across the another plate. In the Indian and Eurasia sector, collision boundary, the Indian plate is going below the Eurasia plate or subducting below the Eurasia plate. Whereas here, the two plates actually going past each other. So this is a different type of motion. We call it strike slip motion at the western boundary of the United States, North America is seen. So that eventually leads to number of earthquakes in the California region, western USA, so which is very vulnerable to earthquakes. And so also the Himalayan region. So wherever this plate motion or the plate movements are, are there, we are bound to get the stress variation in the stress distribution, and finally the strain which is accumulated over a period of time is released in the form of earthquakes. So, and that is the reason why people want to measure how far the plate is moving and how fast it is moving to tell something about the earthquakes and associated the geological phenomena. Again, to take you towards Japan, you can see how the movement is taking place. Japan is one country which has large number of installation GNSS receivers. And you can see those pink lines and the red lines indicate how the movement of the Japanese island is taking place. So there is a variation in the movement, and because of this movement, Japan is also prone to many earthquakes, and earthquakes when that happen in the ocean, we have the tsunami also. So if you look at on our cultural features or the infrastructure like the railway track, you can see how the railway track has moved in this picture due to the fault movement. So somewhere it is very catastrophic, and you can see it very easily, but sometimes the movement rate is so slow, like Indian plate, wherever you are today, so down south or in Himalaya. So everyone is moving, and 5 centimeter per year, that works out to be, you can find out divided by 12, and you will come to know how much millimeter per day you are moving, even today also how much you are moving. So you can calculate, which is not appreciable. You cannot know actually you are moving. Whereas if you look at this infrastructure of the railway track, you can see that yes, movement is very clear. So when it comes down to few millimeters, then it becomes difficult to perceive, and the GNSS is the instrument. So one of the instrument latest, there are other methods of measurement, but currently since 1990s, GNSS has become the default instrument to measure such kind of movement with an accuracy of, it goes to 1 to 2 millimeters. So when you talk about the accuracy in earthquake studies, I am referring to the accuracy in the X and the Y direction. Z direction, the accuracy is relatively poor, But when you set the X and Y direction, the accuracy is a 2 to 3 millimeter. Z direction, the accuracy would be maybe, maybe 2 times of that order, but not significantly lower. So that is also over a period of time one can measure and find out in the Z direction also types of the global navigation satellite system, constellation of satellites, and what is mentioned in this slide, 10 meter or better accuracy, it is mainly for the using a single frequency and without doing any post processing. So that gives you a little poor, the accuracy. But in the geology or the geodynamics or the crustal deformation studies, what we are involved with at IIRS, we look forward to something like less than 5 millimeter accuracy. And we achieve that by post processing and receiving the data in 2 frequency and then doing the post processing with a lot of correction factors which are made available through various global agencies. So we have the Galileo system, GNSS, the popular consists of the Galileo, that is European Union, European Space Agency, and the QZS from the Japan, and GPS, which is popular GPS, is from the US. Navstar constellation, then we have the GLONASS from Russia, IIRS from India, Navig Video from the Chinese. So these are the systems today available, and each one is having around 30 satellites or so. IIRS, we have less number of satellites, but since a regional system, it caters well to the Indian need as well as the the Indian subcontinent need. And so you have more than 200 satellites, and that if you have a dual frequency receiver, if you have the capability to capture all the frequencies, you will get large number of, you'll be able to track large number of satellites, and you can process from each one of them the location, your location, and you can improve your accuracy significantly to reach the objective of less than 5 millimeter, for our kind of study or our kind of applications, what you're discussing this afternoon. Now, to tell you about the number of satellites, what we see, this is an older slide. Average combined GNSS visibility over 24 hours. So that shows that places where you can see around 50 satellites all the time. And relatively it goes lower as you move towards the polar region or to the other part of the world. But Indian region, if you see, large number of satellites are possible because of the the Chinese satellites are operating there, Japanese also operating over there, and we have the ISRO system apart from the global systems, typical global systems, 3 global systems: European, the Russian, and the US. And then we have the Chinese, Japan, and Indian are the 3 regional systems. So these 3 regional systems, 3 global systems, makes the Southeast Asia and the Asian region one of the places where largest number of satellites can be tracked using a dual frequency GNSS receiver. And numerous applications are possible, and we'll be looking at something like natural hazards, real-time earthquake damage assessment and tsunami alert, natural hazard monitoring, space weather, and location-based services, and the national security related applications, precise real-time position anywhere. So these are the applications which are emerging today, and we will look into the geoscientific applications. So first thing is look at the landslides and the earthquake monitoring. And I have just kept few because this is a first lecture, and for you to appreciate how really we work. And so few selected applications I am going to show you with our own data sets, and how this this technology is providing us very, very valuable information, and this information how we actually put to real use. So GPS satellites, you can monitor actually the landslide movement. So landslide movement varies from few centimeter a day to few millimeter. Sometimes it could be catastrophic. Suddenly, the entire landmass will slide. So all that can be monitored if you have a sensor or the receiver on the landslide mass and reference point surrounding areas. And then similarly, the earthquake, there are upliftment and subsidence which happens closer to the earthquake, the plate boundary situation, and some places will go up, some places will move past each other. All that kind of movement, which is very, very dynamic and very, very variable in all the three directions, which is X, Y, and Z direction, can be monitored using GNSS receivers, and it will provide us the response of the crustal movement. So we will see such movement. Now, to monitor such movement, just to give you some examples that how people are doing it. So the prototype GPS fault slip sensor, which has been installed in the California, that is for real-time monitoring of the fault. So geological fault is a weakness, is a line, and along which there is a fracture, and across the fracture, the blocks of the earth are actually moving. Crustal part actually is moving, and it's very, very important to monitor that. And people are using the GNSS system, the GPS, American GPS, to monitor such movements. This is one application which is on real time they have been doing for the earthquake monitoring in California, which is in the western part of the US and very, very prone to earthquake hazard. And now this is how there's a fault which is moving, the yellow dotted line, and we have to have across that fault, and you can see that fault is actually going over a road, and we need to monitor how the fault is moving. So after some time this road will be damaged partly, and then again the repair has to be done. So we precisely need to know the blue dots are the places where it's recommended that if you have a fault which is moving, so across the fault you have to location and put this instrument, basically dual frequency GNSS receiver, and to monitor the deformation which is happening. Now this is a example of how the landslide is monitored. So you can see the landslide mass, and it's an example is in France, and this landslide body has been, there are a large number of antennas on the landslide body, and it is monitored using the GNSS. So this shows that some of the location, there is 0.7, 4, 3, 6, and 8. There is not much movement, but the movement is very, very high for the places like point number 2 and point number 1. So point number 1 and point number 2, actually they have been moving drastically and much more compared to the other points. So such kind of movement can be detected, and you can see always this, in this case, the movement in terms of the meters, because this is a very, very active landslide, but it could be in millimeters as well. And this is one about the dam monitoring. Infrastructure, a dam and the reservoir area. So it's very critical to assess the stability of the dam. So you have a different strategy that, there are 2 rover stations on the, on the dam. They have been located, the 3 rover stations which has been put together. And then we have a RTK, real-time kinematic GPS data collection center. And all these points, the 3 stations, rover stations, which is installed over there, or you can take and keep the instrument there, they have been monitored. So using this monitoring, we can find out what is the deformation happening on the dam with respect to the water storage, which is varying. So long-term, short-term, both deformation can be monitored, and accordingly the dam authorities can assess the performance of the dam, and at some cases the preventive measures can be taken based on this deformation rate. So This is another example, similar. So the most of the dams are being monitored today using a strategy of this kinematic GPS, real-time kinematic GPS, and often the dam, there are receivers on the dam as well as in the surrounding areas, and all this is monitored to look at the deformation on the dam. So you can see that how the water level is recorded and how the water level changes according to the deformation. So the vertical deformation at the GNSS monitoring sites, how these are changing with respect to the water level. So water level goes up and accordingly the deformation is increasing, as you see on the lower diagram. Now we'll come back to the Indian plate. So we have seen that the Indian plate is moving in a linear fashion. And there is a theory, the Indian plate is not only moving in a linear fashion, but there is a rotational component to it. Some kind of anti-clockwise rotational component is also there. This was postulated, and later on using the GNSS analysis and GNSS survey, we have proved that yes, there is a translational motion. Along with that, we have the rotational component, which Indian plate is moving in an anti-clockwise motion. Now, what is happening? This is the scenario we have given from the last 20 million year, 50 million year, how the movement has taken place. What is the present scenario? So it's how it was in 50 million year ago, 20 million year ago, and how it is today. Now, what we have today measurement is of last 30 years. But the last 30 years measurement also shows the similar pattern. And we have very, very precise measurement. These are all hypotheses what has been given by geological observations. But this has to be substantiated by the present measurements, which is possible through satellite. So the very interesting thing emerges because of this anti-clockwise motion. And now what happens is China part, South China, actually moving in a clockwise motion. So China moving in a clockwise motion and we are moving in anti-clockwise motion. The whole thing, we have a translational motion. Because of translational motion, we had a collision. Eurasia plate and Indian plate had a collision at the Himalayan boundary. On top of that, the South China moving in a clockwise and Indian plate moving in an anti-clockwise. The effect of collision becomes much more pronounced at the northeastern sector. Now, that's one of the reasons that why the Northeast India has emerged as one of the most landslide-prone area, which has experienced two largest magnitude earthquake ever occurred on the land on planet Earth is actually located in Northeast. Very interesting that many of you may not know about this fact, but this is true that high magnitude earthquakes, 9 magnitude, 8.5 and all, they normally happen in the sea. Whereas on the land, the two earthquakes of 1984 and 1896 and 1950, both these earthquakes very, very close to 9 magnitude, they have occurred in the Northeast, and primarily attributed to this kind of a complex motion, which is the clockwise motion of the South China and anti-clockwise motion of India within a framework of overall north-northeast direction, pushing by the movement of the Indian plate. So now this kind of movement is critical. Now, whether we see this movement today and what is its manifestation, that also we will look into it. So as I said, there are other paleomagnetic rotations have been also studied using various other techniques. This was a theory which was postulated by the German scientist, and that the anti-clockwise motion of Indian plate, has been observed. Now, if you look at this diagram, it's very interesting. We have here the one is the northwest corner of our Indian plate, blue line, and on the north east side is the red line. So always the red line, the northeastern part is actually moving much more than the green line. So this also tells indirectly that we are moving bit more towards northeast than compared to the towards northwest. So this also supports that the movement, what you see today, is essentially due to this complex rotational component. And earlier it was moving at something like 109 million millimeter per year. It has come down to something like 44, 50 millimeter. And as you go into the Himalaya, still the movement rate reduces. So at the boundary it is something like approximately 45 to 50 millimeter. Then it goes because of the collision, it cannot move. So the movement rate reduces as we cross the Himalayan and start from the Himalayan mountain front and go into the Himalaya. So this is also the northwest corner and the northeast corner, both show a differential rate of movement. And this is what I was showing you, the Chinese South China, how it was moving. Numerous studies have been carried out, and all the studies have brought that there is some kind of a the movement which is clockwise and moving in the southeast direction. And if you look at the western side of the China, northwest Himalaya and western side, they are moving towards west, and here it is moving towards east, something like pulling apart. So that is what observed over the Tibet region, and that's one of the reasons that why there are a lot of fractures and a lot of lakes have been formed, and some of these lakes actually is having a lot of lithium, so which is used for the mobile industry, and Chinese are the one of the leading producer of lithium because of those lithium is seen in those lakes actually. So very interesting. And what we see here, the movement fact, the movement and its impact on the earthquakes. So this is what gives a clear picture, more or less clear picture. We have a rotational component, clockwise motion of the China, and the Indian plate motion is not emphatically proved. Some Indian scientists have indicated, but our group is the first group to very, very emphatically to prove that it is the anti-clockwise motion, which is responsible for several things. And so this is something like a unique finding of the Indian Institute of Remote Sensing, and its impact. So you can see our installation, and we have done the installation at some places. Still installation is proposed. Some we have completed. So we have the seismic stations, and we have the permanent GNSS station, how it looks like. So we have a very systematic way of making the permanent stations on which the receiver is there. If you go to Japan and all, they don't require security. They're all national monuments. They just it doesn't look like a big. They just put the instrument wherever they feel like, and here we have to secure it. A lot of effort is required in India. Otherwise, solar panel will be stolen, everything will be stolen. So site selection is also very, very important in our case, and a lot of effort goes in installing the instrument, running the instrument compared to the analysis of the data. So this is our setup, and we have to live with this. So we will now move on to the next slide. So this region, why we are studying in detail, is because of the earthquakes. So this is a diagram which shows the epicenter of the earthquakes. We have major installation at the Mussoorie, Dehradun, Chamoli, all those places we have mentioned. We have our instruments located to monitor these earthquakes. And what does it show? Our data vis-a-vis the data from the surrounding plates. All the data has been analyzed, and it shows some kind of a translational motion, and this is with respect to a motion and in absolute term, with respect to, you can say, the global framework. And we will see now, this is the rate of movement for different stations. You can see We have the north component, east component, and these, the relative velocity, ISC, Hyderabad, then the Port Blair, Mandi, in our own station, Dehradun, Lhasa International Station, Pole 2 again international station. So there are a lot of international stations are there, Australian stations are there, along with our own station we have been analyzing. So all the data from different stations can be analyzed together, and we try to find out how the plate motion is. You can see this Indian plate IISc Bangalore 54.54 and 54.68, that goes for this Hyderabad, and our Andaman area that moves at 19.55. Lhasa moves at something like 48.59. So all these places have variability, and you can see that the double decimal level accuracy has been achieved by long-term observation. And looking at some of our, we not only the permanent station, we have also the temporarily, we occupy certain locations, and for 3 days to 5 days, and 24/7 we observe the data. Every 6 months we go there, and also very cost-effective manner, because we cannot install everywhere the permanent GNSS system. So it is very, very costly, and that's the reason we have a combination of permanent station and also the campaign station. So campaign mode means we will go for 3 days, 3 to 5 days, 24/7 observe, and every 6 months we'll go there, then find out what is the velocity of that location. So this also gives us, a lot of information which is presented here, 46 millimeter to 58 millimeter, and it varies, across the region. So this is how the IISc Bangalore shows from 1996. If you look at the plot, the data, if you plot up to 2010 or 11, you see linearly, it is constantly moving on the move. So this is what the approximate the global scale, the velocity, it works out to be in this case 35 millimeter. This is only one aspect of it, what they have mentioned on a global scale, but we have mentioned with respect to our ITR framework, it is around 50 millimeter. And now, what you have done in this case, we have with respect to Dehradun, we try to see how is the movement taking place. Earlier it was a global framework. Now with respect to Dehradun, then we see that the Hyderabad and the IISc Bangalore are moving towards east. So this actually revealed that we have a strong anti-clockwise motion. So this analysis, and very emphatically then we related with the earthquake in this region. I'll show you the other aspects also. And if you keep this Bangalore or at the center, then the Dehradun is moving in a towards west, and Bangalore will move towards east. So that makes that anti-clockwise motion very, very accurate. Some of the places of in the Himalaya, actually, they are moving towards south, because we are keeping this Dehradun or the Bangalore as the center. So because of the collision, the areas are not able to move. So we get a feeling that it is moving towards south. So that is because of the relative rate of movement reduces significantly, and those areas look like falling back towards south. So now a very interesting thing is this kind of anti-clockwise motion, what it leads. So some kind of, everything is pushing towards east. So new streams being developed, and a lot of evidences, satellite-based evidences we have seen, new streams being developed, and the stream joining points shifting. So its dynamics is not only that, you measure it through the instrument and you see it, but also you see in the form of drainage migration, the first order drainage, second order drainages, which is very, very susceptible to this kind of change. That also shows in last 30 years time how they are migrating. Very interesting. Everything is moved from the eastern side is getting affected, because things are being pushed towards east. So there is a river at the frontal part of the Himalaya, and we see The eastern bank has been eroded significantly. There is a whale actually. The whale is standing today. It is of during the Mughal time period whale. All the sediments have been eroded. So what it tells that if you have a Himalayan stream, and because of this eastward movement, the eastern bank will be more vulnerable to erosion compared to the western bank. That's very interesting. If you are doing the flood protection, and you have to emphasize only on the eastern side, not on the western side, because of this observation. So the disaster monitoring or the disaster management strategy can be redefined. Looking at this observation and correlating with the satellite-based observation and the field observation. It's very important to compare the field observation with the satellite-based observation. Satellite means satellite imaging, what I'm telling, and with the positional observation, what we observed from the GNSS. So what the German scientists have done, some other scientists have done, those work is also kept at the back of our knowledge base, and look at the GNSS observation, satellite-based observation of the last 30 to 40 years. Your satellite-based observation, you can go a little more in a time scale compared to the GNSS, which is only 30 years data you have today. So put all that together to tell the story that the eastern part of a certain rivers are more vulnerable to flooding than the western part. So this is how the science progresses. And we also have, the calculated, my screen is not fully seen to, yeah. So we also calculate the relative velocity, and based on the relative velocity, we try to find out how much the crustal shortening is happening below the Himalaya. So we know the Himalayas, are rising because one is colliding, Asian plate is colliding below the Eurasia plate. Because of that, crustal shortening is happening. So what is the rate of crustal shortening? More crustal shortening, there is a possibility of more earthquake. And this also we have measured. And yeah, right. So what important findings we see? The deformation across the Himalayan frontal thrust, which is a measured discontinuity or the fault plane. We see something like 11.4 millimeter a year. And the Indian plate shows, slows down from 54.47 millimeter to 48 in the Himalayan region. And in the Himalaya region, we have a crustal shortening of something like 17 millimeter per year. So 17 millimeter per year, the Himalaya is squeezing. So because of that, the rise, what is the obvious thing is the rise in the Himalaya. So wherever the compression of is shortening is high, so that is where we expect the earthquakes. Now, very interesting thing, 2015, we had a devastating earthquake in Nepal. I am showing you the SAR interferometry, which indicates how the deformation took place. And now we'll cross-check this data with the data which has come from the GNSS. So you can see that this movement, this periodic movement was there in the GNSS. So GNSS data varies across the season because of the water loading, because of the monsoonal rain. We have an enormous amount of water loading because the water loading actually areas subside. Then once the monsoon is over, they'll go up again. So even you may not realize that this happens because of the hydrological loading. The upplement and subsidence also varies, of course, by few millimeters, but nevertheless it happens. But that was happening in the Nepal also. But suddenly, because of the earthquake, we have a sudden shift. This shift was significant. 156 millimeter of shift was there, and all these stations are operated by the United States, America, that is Caltech. So they shared the data, and we looked into it. How much actually the areas have moved? So 156 millimeter, movement has been recorded because of the earthquakes. Things were uplifted somewhere, it was subsided. So the same thing also we had observed using the interferometry synthetic aperture radar. But this is ground-based observation. So it's extremely reliable, and we can see how the ground has responded to the earthquake and different parts. Luckily, they had a lot of good instruments, and that could measure this. Now we'll come into very interesting thing. This is the total electron content. As you know, the dual frequency, two frequencies, you know, the L2, L5, always two frequencies are used to find out the location precisely. And this dual frequency we are also using to find out the total electron content in the atmosphere. In the atmosphere, in the ionosphere. And this total electron content in the ionosphere, just a minute. I hope you are able to see that. Yeah. Just let me just see. Is it okay? You are able to see the slides and the presentation? Just to get a feedback. Right. So, okay. And this is what we saw in the Nepal also. Then we are discussing about the total electron content in the ionosphere. And we use the dual frequency. And using the dual frequency GNSS receivers, one more new application has emerged today, that the ionosphere, electron content in the ionosphere, you can measure. So because of the two frequency, there is a difference. There is a some kind of refraction happens, which is dependent on the number of electrons present in the ionosphere. And the ionosphere starts from the 90 kilometer, goes to 350 or so. There are different layers of the ionosphere, and we can calculate the electron content. Electron content is very, very critical for the telecommunication as well as for the earth science point of view. The variation in the total electron due to according to some theory can also tell about the forthcoming earthquakes. So I will not go very deep into it. That is a physical theory behind it. You are encouraged to read these references what I have given in this. A lot of references I have given, and you can download them from the internet, particularly the Friedman. He has some YouTube videos, and you can see that to understand the physics behind it. But we will not discuss much about the physics. It is all given here. We will be discussing about the operational part. So that is important for us from the GNSS application point of view. Right. So due to the earthquake or before the earthquake, a lot of changes happen in the electron in the ionosphere. So you have the lot of other phenomena also happens, and atmospheric gravity waves are propagated, ultra low frequency emissions happen, and radar emission, thundercloud. So many things happen because of the the earthquake, because of the earthquake phenomena. Now you must be thinking that earthquake is such a gigantic effect it has on the planet Earth. So high magnitude earthquake particularly, how can those happen without any effect like this what I mentioned here? But somehow these effects have been less understood with respect to the actual causative factor of the earthquake. And many scientists have tried to understand. Now a unified theory has been given by some scientists, and we tend to believe that with our observation, which is independently we have made observation across the globe. for more than 100 earthquakes we have studied across the globe, because GNSS is a beautiful system. So wherever there is a GNSS system, we can access the data today, analyze with respect to the earthquake. This is also new finding for us, that prior to an earthquake, there are hypotheses that some kind of perturbations will happen in the ionosphere electron content. So let's see that what we have studied so far. And I am not going to show you details about this IGS stations. All this thing indicates the data is available, and this data you can access. So what we are doing right now is analyzing this data. So the ionosphere electron content will vary over a period of time. So daytime it is a maximum, nighttime it reduces because of the solar, the solar wind interaction and the factors which is related to the solar effect. Now there is a particular pattern that the values will increase and decrease every day. It will daytime increase, nighttime decrease. So this systematic pattern is observed for 10 to 15 days. Then we try to find what is the normal variation of this observation at a particular second. So particular second or particular minute you can consider in case of the GNSS. This is the temporal resolution is so high. So we try to analyze this. Some cases 1 minute, some cases 1 hour. In this case, actually 1 hour is considered 1 hour. And so every hour we know what is the maximum variation, what is the minimum variation. So we have a, some kind of standard deviation. So using this, the electron content plus 1.34 standard deviation minus 1.34 standard deviation, we have a lower bound and upper bound. And when we try to plot our electron content, sometimes the electron content will go beyond the lower bound and upper bound. So lower bound and upper bound is decided based on the previous 15 days data. And this is a moving average kind of thing. Every day we'll be proceeding, we're moving with the data and changing this, the standard deviation and other things will be keep on changing. But certainly certain days we'll find this electron content is overshooting or undershooting the lower bound or the upper bound. So this is called the anomaly. Whenever the total electron content overshoots or undershoots, this is the anomaly. Now this kind of anomalous things have been observed before a major earthquake at many places. So this is one earthquake, 7.8 magnitude on 16th of April 2016 at the equator. And as I said, we have the access to global data. Anywhere the major earthquakes happen of 7 magnitude or 6 magnitude, we try to find out, was there any anomaly? This is what the anomaly we see. The value suddenly decreases below the lower limit. And the day it happened, there are 3 occasions, two prominent occasions when the value was 9 days before and 1 day before. These values actually fallen significantly lower compared to the lower bound. And the theory says, physics says, that the total electron content also dependent on the magnetic, the magnetic flux and also the magnetic storm and the solar flux. So those parts are also eliminated using global data sets. So AP index and the F10.7 are the information which rule out the magnetic storm and the solar flare. So high solar flare also can cause change in the electron content. So solar flare and the magnetic storm effect is also ruled out looking at those data sets. So since you're looking at the lower anomaly, the very interesting thing is, since you look at the lower anomaly, these two, magnetic storm and the solar flare, can actually increase. So whenever there's a decrease, obviously the fact is it will not have the influence of these two, the two phenomena. But if these two phenomena are there and there is an earthquake signature, we will miss it because it will look like a normal because the solar flare high and the magnetic storm is there. But during this time period, and it's not only once it comes, so a couple of days it will come this kind of signature, and there is always a possibility that we will be able to capture it. And this is what we have shown, we are able to capture it. And luckily we have entered into we have the solar flare maximum 2012. So now we have a reasonably quiet period, which will be there for another 10 years or so. So during this time period, the magnetic storm and the solar flare won't be much. And this is what's predicted. And in that scenario, actually, we should be able to see this, the low values prior to an earthquake. So we have seen successfully before 9 days, 1 day, or one earthquake. I'll show you the other ones. Now, interesting thing is, when you look at this global data set, try to find out, in 2 dimensions, the same philosophy we extend into 2 dimensions and try to find out what is this anomaly and where is the earthquake epicenter. Is there any correlation? We see a very, very interesting and very significant correlation between the location of the epicenter and the center of the anomaly. This is interesting, and this becomes a new finding for us. Using the GNSS dual frequency data, total electron content has been identified, and we're able to measure every minute, every second, every 15 seconds, every 1 hour, and then we see how it is varying, in 2D. So the spatial and temporal variation has been observed, and the anomaly has been picked up, and we see a good correspondence between the anomaly and the earthquake epicenter. And since the data resolution is very, very low, it's 500 kilometer by 250 kilometer. So in this case, the accuracy is something like 250 kilometer or so, because of, it's almost a 1 pixel. So I will see how to show you also how to increase this. Now, what accuracy what we got from various earthquake events we have analyzed: 190 kilometer, 250, 254, 197. This is the kilometer accuracy what we see, around 200 kilometer or 150 kilometer between the actually estimated earthquake epicenter and actual earthquake epicenter. So this shows that before 10 days, 5 days or so, you are able to know the earthquake is coming, and coming at a place which is just 250 or 150 kilometers away from your prediction. It's a significant achievement, I would say. It was very, very thrilling moment for us when we came across this. And many scientists have worked, but the way we have detected the anomaly, there are a lot of theories where there are a lot of speculations and all these things, but there is a way to detect. And this is what our team actually did. Similarly, we checked for the Indonesia earthquake. Story is same, 8-7-2 days before we see the anomaly. Rule out the effect of the solar flare and the magnetic storm, and correlate successfully with the epicenter. I'll show you that. You can see the epicenter location and the anomalous zone location. So again, it's very, very close. Now, Sumatra earthquake, another earthquake we have considered. 6 days before, we have seen a significant anomaly of 7.8 magnitude earthquake, and we also see very close to it epicenter and the anomalous zone. Now, we will look at the Indian Himalaya. So far, we have seen good results from the equator region and the Sumatra, Indonesia, all those high vulnerable locations. And when you look at the Indian region, Himalaya particularly, with respect to 2015 earthquake, will show that. Couple of earthquakes we have taken of 4.9 magnitude Pipalkoti earthquake. There are some 7.8 Nepal, 6.7 Nepal. So Nepal earthquake 2005, 2015 when it happened, 3 consecutive events took place. So one was on the 25th of April, one was the 2nd day, and then another one on the 12th of May. So all those events have been analyzed with respect to the electron content variation in the ionosphere. Now what we see, clear-cut variation. Now this is using not the global data, using our own instruments, what you installed over here. So there are the blocks what I have shown here, the round circle. So the anomalous things have been observed before a couple of days, and very significant anomaly also we are seeing before 14 days. So this is using not the global instrument, our own instruments, what you installed in the Garhwal Himalaya. So both the earthquakes we have studied, all the 3 events that we have studied using 2 primary stations. What we had, one we had at Dehradun, another was at Chamoli, and So global data set also we analyzed. So it shows 14 days before, 4 days before, and 1 day before we had the anomaly. Now, when you look at the global data, which is low resolution, same also it revealed. Before 14 days, we had a significant anomaly. We had also seen our own data. This is the global data. Global data is a reprocessed data at a much coarser resolution using the global IGS network. And so this also showed, and this helps actually to identify the location of the epicenter. So location of the epicenter and the actual epicenter were very, very close, offset by 277 kilometers. And as I said before, this is mainly due to the low resolution of the global data set. Since we had the local data for the Nepal earthquake, I'll show you, we analyzed that. This is the data which was given to us by the Caltech. And okay, because our instruments in Nepal and our instruments, we don't have instruments over there. We have only the Indian part. So when you analyze these local data sets and apply the same methodology, the accuracy what we got came down to almost 35 kilometers. So that means what 15 days before or 14 days before, it is possible to know the earthquake is coming, and the expected epicenter is 35 kilometers from the actual, which was estimated, which was calculated. So that shows that significant improvement over the, the forecasting or I will not call it an early warning system so far, because early warning means you have to tell about the magnitude, location, time, very, very precisely. So I would name it early detection, but it's a significant move in that direction. What we saw for the Nepal earthquake. Now, for the remaining many earthquakes we have also studied, it's not only one event, and we see a similar, anomaly before so many earthquakes we have studied for the Himalayan region. So more or less the story is early detection is by tech low, succeeded by tech high or no high, 1 or 17 days before, on an average 3 to 15 days before the event. And successfully we have tested this over last couple of years, and every time we say that earthquake is possible, and it is happening. And I hope I have some data to show you. And then not only this electron content change what you have reported from the GNSS observation. One paper by the Moria et al. In the Journal of Geophysical Research also published. That is about the very low frequency wave propagation. It is mainly due to the VLF sensors are there, transmit the wave. It comes to, goes beyond the ionosphere, again comes back, received in Allahabad, India, various locations. That also showed some kind of variation prior to the earthquake, a day prior to the earthquake. So it's not only our observation, which is GNSS based. Other people also have reported similar, the electromagnetic wave propagation and variation, prior to an earthquake. So that indicates that there is there are ways of looking at the precursors of earthquake, and if you put system together, it is possible to get to know more clearly and more precisely about the earthquake. And this is what the research we are carrying out, and now we have joined hand with the Moria et al. To work further in this direction. So let me just see. Yeah, the same thing also we have seen for the there was the event on the 6th of February 2017. So our data and this very low frequency wave propagation data also showed similar results. So 2 events at least we have studied, and now I am showing you something from our database. And very interesting that there was an event on 24th of September, 6 magnitude Mirpur earthquake in Pakistan, and all our instruments measured, detected anomaly prior to that, and this anomaly was very, very high at the location which was very, very closer to the epicenter. And as you move away from the epicenter, the anomaly gradually decreases. So that shows that the anomaly what you have detected is actually related to the earthquake, and if you are able to detect this anomaly, you can actually tell about the forthcoming earthquake. So, right. So this we have come to the end of this presentation, and there are some references. And if you have any question, I'll be happy to take that. So thank you very much for your kind attention. And I'm sorry that in the beginning there was some technical glitch, delivering the talk or internet were not working and something went wrong. You can go through the lecture, this material and look at these publications. And if you have any questions, you can ask me now as well as afterwards also. So thank you once again for attending to this talk. Thank you.